In this video, I am going to talk about Mini Project 3 and give you tips and tricks. So in Mini Project 3, we are working with rational equations and we are going to apply it to a medical example. And so what I show you here will help you for what you'll be asked to do in the mini project. Okay, so modeling concentration of anesthesia in a patient. So anesthesia is given to patients who undergo surgery or some other kind of operation. The anesthesiologist, or the one giving the anesthesia, must be very, very careful to make sure it's the correct dose. If the patient is not given enough, they could wake up during the operation, or if they're given too much, it's really dangerous. So guess what? The equation used for this is a rational equation. Let's take a look at an example. So suppose the equation for a particular patient is given by y equals 4t over t squared plus 1. So we've got the rational equation, we've got variables in the numerator and denominator, or polynomials in the numerator and denominator. So t is an hour since the dose. So 1 hour later, t would be 1. 3 hours later, t would be 3. And y is in milligrams per liter, and that's the concentration of the dose in the bloodstream. Okay? So that's measured in milligrams per liter. So let's talk about what milligrams per liter actually means. So milligrams is the units of the dose, and blood is measured in liters. So what I have off to the right is a 2-liter bottle of soda. Cherry Coke's my favorite. So that's what I put here. But I picked 2 liters because it's an item that we could possibly be familiar with at the grocery store, in your home, something you've had before. Okay, so this is 2 liters. And pennies are 2,500 milligrams. Okay, so if pretending that my penny models my dose and my soda models my blood, if I were to drop this penny into this 2 liter and it dissolves, the concentration would be 2,500 milligrams per 2 liters. And if we simplify, 2 divides into 2,500 to get 1,250 milligrams per liter is what we're looking at. Okay, so that's what that concentration means. The units do mean something here, and this is just a visual to help with that. Okay, so let's talk about working with the equations. So we have y equals 4t divided by t squared plus 1. So the first part, find the concentration in milligrams per liter 1 hour after the patient receives the dose. Okay, so we're given time, and we're being asked to find y. So what we would do is we would plug 1 in for t, and simplify. So after 1 hour, the concentration in the blood would be 2 milligrams per liter. Okay. Number 2, after how many hours will the concentration be 1.789 milligrams per liter? Well, we're given concentration and we're asked to find t. So we plug in 1.789 for y, and then we solve for t. This would be t squared plus 1. Okay, so when we solve for this, you solve it like you would a rational equation. You can see this as cross multiplying, where we have a fraction equal to another fraction, or you can see it as multiplying the denominator to both sides, or you could see it as getting the same denominator and crossing them off. Okay, but now what I have is 1.789 times t squared plus 1 equal to 4t. Distribute, and I'm going to come down here, 1.789 t squared plus 1.789 equals 4t. What kind of equation is this? It's a quadratic equation. So you'll move everything over to the left-hand side. Should have given myself more room. And this is equal to 0. So here you would probably use the quadratic formula. You may get 2 values for t. Pick the one that makes the most sense. So in the first question, we found that after 1 hour, the concentration is 2 milligrams per liter. And now we are asking at what time will the concentration be 1.789 milligrams per liter. So it's probably, just make sure you're picking the correct t value that goes along with that. And what I should mention is for this example, we'll get 2 t values, but in the mini project, you're going to be filling out a concentration log, so you'll have some guidance. So for instance, let's say we were doing the concentration log Okay, and here we have minutes, and here we have concentration. We just found that after 1 hour, it would be 2 milligrams per liter. Okay, and then let's say I had 1.789 milligrams per liter, and then I had like 3 hours. Oops, that didn't need to be there. And then I had like 3 hours here. Okay, so the value for T that you would pick would be between 1 and 3. There are 2 T values that will give you 1.789, but again, when you're filling out the concentration log, pick the value that makes sense according to the log. Okay, more working with the equation. So number 3, the anesthesia is no longer effective when the concentration falls below 0.8 milligrams per liter. Based on this model, when will the patient wake up? So again, you're given a Y value and you're asked to find T to do that. Okay, so you'd have 4T over T squared plus 1. We are really looking at when is it less than 0.8. You can set it equal to 0.8 and then say, okay, after that amount of time, the patient will wake up. Okay, and let me give you the answer to this one. If you were to solve it, you would get 4.79 hours. Okay, so good amount of time that it would work or be effective. Okay, so if the procedure is supposed to last 4 hours and 51 minutes, will more anesthesia be required? So for this one, be careful. This is 4 hours and 51 minutes. It is not the same as 4.51 hours, okay? 4.5 hours is 4.5 hours, which is 4 hours and 30 minutes. So be careful. This is 4 hours and 51 over 60 because our whole is 60 minutes. Okay, so this would be 4.85, which makes sense. 51 minutes is close to the full hour. Okay, so in this case, yes, more anesthesia would be required. The patient would wake up after 4.79 hours, and the procedure is supposed to last 4 hours and 51 minutes, which is 4.85 hours. Okay. The last thing that we'll talk about is you will be asked to graph the equation and upload your graph. Use Desmos again, and remember you might have to use X instead of T. There was a video on this in Mini Project 2 if you need to look back. But number 5, if the concentration is more than 3 milligrams per liter, then it's dangerous. What is the maximum concentration the patient had in their bloodstream? So the maximum is the highest Y value in the graph, okay, or you can think of it as a peak. So we have a peak right here. It occurs at 1, 2. Remember our X variable or our independent variable is time. So this is 1 hour, and the 2 is our concentration. So the maximum that a patient will have at their bloodstream would be 2 milligrams per liter, so not in the danger zone. Okay, so that's what the maximum is there. As you're working on the project, if you have any questions, let me know.